Welcome back, students, to the second part of the lecture. We are looking at Henderson-Hasselbalch equation, that the shape of the titration curves for all weak acids is described by Henderson-Hasselbalch equation. This equation simply restates the expression for the ionization of a weak acid as shown in the following derivation. Ka is equal to H plus then A minus. That is for this. This acid will break down to release a proton and will release a proton or acid and what? A base. So after solving for hydrogen ion concentration, whenever you see this bracket, it means concentration. The equation now becomes hydrogen ion concentration is equal to Ka, that is the acid dissociation constant, then the acid which is formed, acid over the conjugate base. That's conjugate acid over the conjugate base. This is the conjugate acid over the A, which is the conjugate base. But we don't involve the main acid, we just involve the weak acid and its conjugate base. So this and this. So the denominator over the numerator. Then take the negative logarithm of both sides. So if we take negative log of this, we get this. Negative log of Ka, we get minus Ka. Negative log of weak acid over weak base, we get this. After substituting pH and pK into the equation, it becomes, so pH by definition is negative log of hydrogen ion concentration. So we substitute pH there. Whenever we see negative log of hydrogen ion concentration, we put pH. Whenever we see minus log of Ka, that is a definition for pKa. Minus log of hydrogen of weak acid over weak base. That one we leave it like that. Finally, the Henderson-Hasselbalch equation results after mathematical manipulation of the log term. So this is the log term. So that is what the man or the scientist manipulated. So this is the log term. So what we'll do is that we'll bring this weak base to the numerator. Then we'll bring the numerator, which is the weak acid, to the denominator. So we turn this one upside down. So the leg goes up and the head goes down. So now instead of having the numerator having HA, it now becomes what? A minus. That is weak base concentration over the head, which is the weak acid concentration. So when you turn this upside down, then the negative sign here becomes a plus. Okay, so by definition, pH is equal to pKa plus log conjugate base over weak acid, as we described earlier on. Alternate version of Henderson-Hasselbalch equation for a base buffer is, instead of pH is for acid, the pKa whatever is for acid, but the pOH is for base. So base also has its dissociation constant, that's Kb, plus log of salt plus log of salt over base. So this one is a salt. It's a salt. It can be NaCl over NaOH or over OH. Okay, let's tackle buffer capacity. When we say buffer capacity or buffering capacity, it is the amount of acid or base that a buffer can neutralize. For instance, if I have a buffer which can neutralize 10 mils or 10 centimeter cube volume of an acid, and I have another one which can neutralize 1000 centimeter cube of the same acid, then which of these buffers has a strong buffer capacity? You can pause this video, think about this question and answer it. Okay, you can now resume the video. So the one with the buffer that was able to buffer the 1000 centimeter cube of the acid has the highest or very strong or the stronger buffer capacity than the one which was only able to buffer the 10 mils. The buffering range is the pH range the buffer can be effective. Okay, so let's come to calculations. These are very important, and it's very important that you have to know how to calculate all the questions over here, because you may miss some of them in your final exams. Question A, what is the pH of a mixture of 0.042 molar sodium biphosphate and 0.058 molar of sodium phosphate? We use the Henderson-Hasselbalch equation, which we'll express here as pH is equal to pKa plus log. Conjugate base, always remember, is the base over the acid. You have to choose this formula. In this case, the acid, the species that gives up a proton, the acid is the species that gives out the proton. The acid is this because it has more protons. The hydrogens are 2. Here, the hydrogen is only 1, so this is the base. This is the acid because it has more hydrogens. So it's represented here. This is the acid. And the conjugate base, the species that gains a proton, is HPO4 2-. By substitution, we get a concentration of acid and conjugate base and the pKa. So the pKa is given as 6.86. So we have pH, this is the formula. So we have pH is equal to 6.86 plus log of the conjugate base, which is this, over the conjugate, over the weak acid or conjugate acid, which is the one with more protons, H2, more hydrogens, 0.042. So by calculation, we get a neutral pH of 7. Question 2. What is the pH of a solution that has hydrogen ion concentration of A 1.75 times 10 raised to the power minus 5 mole per liter? I will solve only the first one for you. So let's begin. The same preamble follows for all the questions there. It's from A to D, the same preamble. So I'll solve the first one for you. Know how to solve the rest. So you can pause this video, then write the questions down and solve it. All the questions you need to solve is going to be the second assignment. Make sure I'm solving only the A. So you follow my example and solve the rest. I will solve this 1.75 times 10 to the power minus 5 mole per liter. Solve for B, C, and D. And go through all the questions that will be following. Make sure you solve everything and present it as the second assignment. Okay, so pH is equal, by definition, pH is equal to minus log of hydrogen ion concentration. So pH is equal to minus log of what? This one, you say, what is the pH of a solution that has hydrogen ion concentration? So it's provided here. So, and the definition for pH is what? Minus log of hydrogen ion concentration. So minus log of this concentration. So pH is equal to minus, so when you run this, you get minus 4.76. Then minus, so you get 4.76. So you can solve for, it seems, did I solve for B? No, I didn't solve for B. Okay, so B, we also have, what is the height? So solve for B, C, D, pause the video and solve them. What is the hydrogen ion concentration of a solution with a pH of A 3.82, 6.52, C 11.11? So let's start. pH is equal to minus log hydrogen ion concentration. Hydrogen ion, so we make this hydrogen ion concentration the subject. So when we make this hydrogen ion concentration the subject, the pH now, the log now becomes 10. We represent this as 10. So the 10 will go and carry the pH. So we can see 10 has moved, the pH has transformed to 10. It has gone to carry this pH term. So we have 10, which is the log, the same as the log, carrying the pH here. But you know, when it was going, it has a negative sign here. So to take the 10, the log, which is 10, will carry away or take the negative sign along with it to go and carry the pH. So it will leave the hydrogen ion concentration standing alone. They are divorced. So hydrogen ion concentration is standing alone. So hydrogen ion concentration is equal to 10, which is carrying the pH with this minus sign. So hydrogen ion concentration is equal to 10.8, 10 raised to the power, the negative sign is there already, then you just go and carry A and come and put it there. So you click this on your, play this on your calculator to get this result. Another preamble: calculate the pH of a dilute solution that contains a molar ratio of potassium acetate to acetic acid, given that the pKa is equal to 4.76. So you solve, I'm going to solve for A, you pause the video and solve the rest. So acetic acid ionizes according to the following equilibrium equation. So this is acetic acid. It will break down to produce acetate and hydrogen ion. And according to the Henderson-Hasselbalch equation for acetic acid, pH is equal to pKa plus log of the base over the acid. So this is the base and this is the conjugate acid. This is a strong acid, that's not it. This is the weak acid, weak base. So weak base first, that's the numerator. Then weak acid, that's the denominator. So when you substitute, like I said, pKa was given to us. pKa was given to us as what? 4.76. So when we follow through with it, we have what? Let's substitute into this formula. We have pH is equal to pKa, which was given 4.76, plus log. And this ratio, the base over acid was given to us. Let's go back. So that is, calculate the pH of a dilute solution that contains a molar ratio of potassium acetate to acetic acid. So we have 2:1. That's the potassium acetate is the base, then acetic acid is the weak acid. So 2:1, 1:3, 5:1, 1:1. So you follow through. So this is what's going to happen. So when you substitute, we just substitute the ratio inside. Then we click on our calculator to get 5.06. So this is an acid. Instances in which pH is controlled. It's very important that we control pH. Heartburn is those who have ulcer. You can see that whenever they are there, they will feel some burning sensations in their chest area, meaning that there is some acid reflux. There is a flow back of acid from their stomach into their esophagus. So they fill these acid burns. So it's very important. That's why we give them omeprazole. That is a proton pump inhibitor or acid production pump inhibitor. The stomach has acid production pumps which produce the acid. So you inhibit this acid producing pump so that they will not produce more acid. So we use omeprazole. So when we are planting vegetables and flowers too, you have to control the pH of the environment. Fish tanks and fish ponds, you have to control the pH or else all your fishes will die. The blood pH is around 7.4 or 7.5. If the pH becomes more, then the person's body is prone to infection or the blood becomes infected. Then we say that the person has septicemia or septic shock. Then if it is very low, the pH is very low, we say metabolic acidosis, and this happens in diabetics or people who are starving and the rest. Acidosis is very bad. It comes with a lot of symptoms: vomiting, diarrhea, headache, dizziness, and the rest. It's not easy. Then swimming pools, as I said. This is the bicarbonate buffer system of the blood. You will do this one in chemical pathology, so don't worry. Bicarbonate buffer system will not come into the exams. You can just read it for your own relaxation. So when we say pH optimum of enzymes, this is the pH at which the enzyme can be able to operate well. This is the pH in which the enzyme is able to survive. So for instance, if you have pepsin is located in the stomach. So it is an enzyme that loves acid. The stomach produces a lot of acid, and pepsin is an acid-loving enzyme, and it digests proteins in the stomach. So it is in the acidic pH of 2. When we take trypsin is produced by the pancreas, and trypsin is having a pH almost neutral. Then we have alkaline phosphatase, is one of the enzymes that is produced in the liver, especially when serum level or blood level of this enzyme is very high. It means that the liver has developed a problem or the person is hypertensive. This alkaline phosphatase, by name, the alkaline means basic or base. So it means that the alkaline phosphatase loves acidic environment. It loves to stay in an acidic environment. That's why you see the highest percent maximum activity or the enzyme activity of this alkaline phosphatase. At the highest enzyme activity requires a very high pH. So it's a basic or a base loving enzyme. The enzyme loves to live in a basic environment. Okay, so this is just examples for our relaxation. This one, hydrogen chloride reacts with water to produce hydrozonium ion plus chlorine or plus chloride ion. Sodium hydroxide in water produces sodium ion and hydroxide ion. Sodium hydroxide plus HCl produces salt. That's when you react an acid with a base, you produce salt and water. Acid plus base yields type of salt and water. Ammonia plus water yields ammonium ion and what? Hydroxide ion, which is a base, so acid and base. Okay, what is a salt? You will get to some age and they will tell you that don't eat salt, or you can see that your mother and your father are not taking salt, or they are taking salt in moderation. What is so unique about salt? A salt is a neutral substance produced from the reaction of an acid and a base. So you can see from the previous slide a salt is here when this base NaOH, it has OH group, this one has H group. When they react, they form salt. That is sodium chloride is salt. That's the salt we take in the house plus water. So acid and base react to form salt. So a salt is a neutral substance produced from the reaction of an acid and a base. It's composed of the negative ion of an acid and the positive ion of a base, like I've earlier on explained. One of the products of a neutralization reaction is salt. Examples of salts are sodium chloride, potassium chloride, magnesium sulfate, sodium phosphate. Neutralization reactions. A neutralization reaction is the reaction of an acid with a base to produce salt and water. So when an acid reacts with a base, so we have an acid here, sulfuric acid, reacting with sodium hydroxide, which is a base. So acid and base forms what? Salt. That's sodium let's say sodium sulfate, then water. So digestion and pH. Digestion is a process by which foods are broken down into simpler substances. Mechanical digestion is physical process in which food is torn apart in the mouth. Chemical digestion, chemical reaction in which large molecules are broken down into smaller molecules. So in the digestive system, in the mouth, the pH is around 7. Saliva contains amylase, an enzyme which begins to break carbohydrates into sugars. Stomach pH is around 2. So proteins are broken down into amino acid by the enzyme pepsin. And like I said earlier on, pepsin is an acid-loving enzyme. It can live in the acidic pH of 2 in the stomach. Small intestine has a pH of around 8. And most digestion ends here. Small molecules move to bloodstream towards cells, that is, after being digested here, they are transported through the hepatic water vein to the liver. That's the nutrient for distribution to the body. Thank you very much. Please try and do all the assignments. You know, I solved the first question, the A. So try and solve for B, C, D, and whatever. Present this assignment to me on Friday. Then I will communicate to you in the next lecture as to whether we are going to have a quiz on Friday or not. So you can bide your time and wait for the biophysics lecture. Thank you very much.